Okay, welcome to the fifth example in the chapter of strain. The question reads, the stress strain diagram for a stainless steel alloy is shown in the figure below. A rod made from this material is initially 800 millimeters long at a temperature of 20 degrees Celsius. After a tension force is applied to the rod and the temperature is increased by 200 degrees Celsius, the length of the rod is now 804 millimeters. Determine the stress in the rod and state whether the elongation in the rod is elastic or inelastic. Assume the coefficient of thermal expansion for the material to be 18 times 10 to the power of 6 in units of 1 over degrees Celsius. Okay, so right off the bat with givens, I can see that I can define two states for my type of system in this question, and more specifically the bar. So I can define a first state where like nothing's happening, right? So we just have the original length. So we can say the length at state 1 is 800 millimeters, right? And the temperature is 20 degrees Celsius. And I can also define a state 2. And my length at state 2 will be after the factors that affect the elongation happen, right? So the question says that after a tension force and after a temperature increase, my new length is basically 804 millimeters. And what did we say this is caused by? This is caused by two things. It's caused by a tensional load, right? And it's caused by a temperature increase. So temperature increase. And it's increased by 200 degrees Celsius, so my new temperature is 220 degrees Celsius. Okay, so this is a good starting point, but we're going to get more specific, right? We want to define specific values, okay, and they're pretty straightforward. So we can define something like, I don't know, the elongation, right? The change between state 2 and state 1. And what is that elongation? We'll call this elongation total, right? It's simply 4 millimeters, right? So 804 minus 800. I can further break this down into its components, right? This is the total elongation of the bar, but what is it made up of? Well, it's made up of two factors, right? It's made up of the elongation caused by the load and the elongation caused by the temperature increase, right? Simple as that. So we can state that, right? We can say that the total elongation is 4 millimeters, but it's caused by two factors, right? There's going to be a portion of the elongation due to the load and a portion of the elongation due to the temperature increase, and that's going to result in a total elongation of 4 millimeters. And this is the equation we're going to use mainly in this question, and we're going to derive, or not derive, but like basically make a proportional relationship, because we know strain, for example, is equal to delta L over L, right? So therefore, strain is proportional to deformation or elongation. So what we can say is strain total is equal to the strain caused by the load plus the strain caused by the temperature, right? Beautiful stuff. So actually, let's write that down. This is skipping ahead because it's a very exciting question, but we'll write it down in givens, no harm. So the total strain, and it's the same concept which we described here. The total strain is equal to the strain caused by the load plus the strain caused by the temperature increase, or the thermal strain. Okay, before we start, because I'm tempted to go into this and we can solve the question just from this, yeah? But we'll do it in proper steps. What else are we given in the question? Well, we're given that we have a thermal coefficient of expansion, or coefficient of thermal expansion of 18 times 10 to the power of negative 6 in units of 1 over degrees Celsius. We've never dealt with thermal strain before, so let's define that equation. Thermal strain is equal to alpha, the coefficient of thermal expansion, multiplied by the change in temperature. And the change in temperature in our case is just 220 minus 20, so 200 degrees. But we'll get to that when we get to that. What else? We are given the stress strain diagram. Okay, I keep wanting to jump ahead. But there is something we can describe on the stress strain diagram, and that is how we characterize the elastic region, right? The elastic region is defined by Young's modulus, and Young's modulus is equal to the yield stress over the yield strain. We can easily find those values, and they are namely 400 divided by 0.002. If you do this calculation, you will get that your elastic modulus is equal to 200 gigapascals, or 200,000 megapascals, right? So if we do find that, for example, our strain or stress is elastic, we can use this relationship to find one of our variables, right? But again, we'll get to that when we do, yeah? So we have an elastic modulus of 200,000 megapascals. Okay, I think givens is all done. We can move on to unknowns, right? So in this question, we're trying to find, let me write this first, unknowns. In the second last sentence of this question, it asks us to determine the stress in the rod and state whether the elongation in the rod is elastic or inelastic. So we can simply write that down for givens. We want to find the stress. What kind of stress? We're going to get to that in just a second. This is where the thinking comes in, yeah? We want to find the stress, and we also want to find whether the elongation is elastic or inelastic. So what did I mean when I said, what type of stress does this question want us to find? Like, are there more, like, obviously it may want us to find the total stress, right? It wants us to find the total stress acting on this bar. Well, I would argue not exactly. The question isn't written like properly, because if you want to think about it, if you look at this equation right here, I can derive, or I can bring from this equation, I can determine that I'm going to have a total stress acting on my bar or beam or whatever it's called. I don't know what it's called. Acting on my rod, right? I'm going to have a total stress acting on my rod. I'm going to have a stress on my rod due to the load, and I'm going to have a stress on my rod due to the temperature increase, right? I can deal with all three of these stresses. I can find each one separately. The one that needs the most calculations and actually needs you to think, basically, is finding the stress due to the load. Why do I say that? This and this you can find, I'll put a timer on, bro, like we can find it in 30 seconds. Like, for example, this strain total. Okay, I know strain is equal to delta L over L, right? Therefore, I can find strain is equal to 4 over 800, right? This is going to end up equaling 0.005. I can go to my stress strain diagram. I can find 0.05, and I can say my stress maybe is 550 megapascals, right? And it's inelastic because it's not in the elastic region. Similarly, for the elastic strain, I can easily find, or the elastic strain, no. I can easily find the stress caused by the temperature increase, because I can easily find the temperature due to the thermal strain, right? Using this formula, I multiply alpha by the change in temperature, so it's literally just 18 times 10 to the power of negative 6 times an increase of 200 degrees, right? And then I have the value here somewhere. You're going to end up getting that you have a thermal strain of 0.0036, right? And then you look on the graph, and then you pinpoint 0.036, might be around here, maybe 490 megapascals. And then all of a sudden you're done. That wasn't 30 seconds, but you get the point. Like, it's very, very simple. This one, on the other hand, it's not as simple, right? And we'll see that in the question. So that's why I'm tempted to think that it said determine the stress in the rod caused by the tensional load, right? And that's what we're going to do, because that one's the most fun, yeah? Okay, so we're going to try and find, and also the stress due to the temperature, it is inelastic, right? Because it's not in the elastic region. Okay, so we're not going to try and find, or we just did, we found stress total, we found stress caused by the thermal increase in temperature. So what we do want to find in this question specifically is the stress caused by the load, right? Okay, beautiful stuff. I lost track a bit. Okay, I went on a tangent, yeah? Okay, how do we go about finding the stress due to the load? Why is it more complicated than, or not more complicated, but just why does it take longer than the other things? Well, to find the stress due to the load, right, I have to find the strain due to the load, right? And the equation for strain is equal to delta L due to the load, right? The change in length due to the load. It's not the total change in length, right? Remember, because we said that the total change in length has a component. It's split into the change in length due to the load, because I'm pulling it, and it's also thermally expanding. And it also has a component where it's the temperature. So my change in length here is not, it's not 400, or it's not 4 millimeters, right? So I have to be aware. to find the stress, I need to find the strain due to the load, and the strain due to the load is the change in length due to the load divided by the original length, L naught. I have the original length, it's simply 800 millimeters. However, I do not have this guy, right? The change in length due to the load. How can I find the change in length due to the load? That's what we're going to do next. And then once we have, I keep going back to this formula, but sorry, I apologize. Once we have the change in length due to the load, and this is L naught, once we have this value, we can find the strain due to the load, right? And then therefore we can find the stress, either from the stress strain diagram, or if it's in the elastic region, we can use Young's modulus, right? So it's much more involved. Finding the stress due to the load is much more involved than the total stress and the stress due to the temperature increase. So that is what we're going to do. That was the game plan, but we will go through it once more. So what did we say? We want to find delta L due to the load. That's going to be a step 3. Okay. I want to find delta L due to the load. What was the equation I derived in Givens? Well, the equation I derived in Givens was this guy. So if I rearrange it a bit, I get that this equation, I'm not going to have enough space. I'll just write it down here. I'm going to get that the change in length due to the load is equal to the total change in length minus the change in length of the rod due to the temperature increase. Right? Beautiful stuff. Do I have this value? Yes, I do. It's 4 millimeters. Do I have this value? Well, no, not exactly, not yet. How can I find it? I know that strain is equal, or thermal strain in this case is equal to the change in length caused by the thermal or the temperature increase divided by L naught. If I rearrange this equation, I can get that the change in length due to the temperature increase is equal to the thermal strain multiplied by L naught. Simple stuff. Delta L due to the load. I'm going to plug in the 4 millimeters minus, let me rewrite the equation. So it's L naught, right? Multiplied by the strain, the thermal strain. So that's just alpha multiplied by the change in temperature. If I plug in my values, 4 millimeters minus, what was the original length? 800 millimeters multiplied by 18 times 10 to the power of negative 6 units like that, multiplied by 200 degrees Celsius. I'm going to end up getting for this equation, if you evaluate this expression, you're going to end up getting that the change in length due to the load is equal to 1.12 millimeters. 1.12 millimeters, right? So of this total deformation, of this total 4 millimeters of deformation, 1.12 millimeters is directly due to the load, right? If I didn't have that increase in temperature, this would be my deformation. But yeah, perfect stuff. And then if you do the subtraction due to this doesn't matter, but just for your information, if you rearrange everything, the change in length due to the temperature constitutes or values up to 2.88 millimeters, right? So that's the change in length due to the temperature increase. Okay, we have this. What did we say we want to find? We said we wanted to find strain, right? We can simply find strain now, and we can say, what are we on, 4? 4, find strain due to the load. I know that strain due to the load is equal to the change in length due to the load divided by the original length, 1.12 millimeters divided by 800 millimeters. And this is going to end up giving me a value of 0.0014 millimeters per millimeter. Perfect. I have my strain value due to the load. Can I find stress? Well, yeah, sure. Let's go check out the stress strain diagram, right? And I'll just put it 0.0014, I'll remember. So our strain value was 0.0014. Can I just look on the stress strain diagram and find it? Well, yeah, okay, this is maybe 0.001, so it might be around here, right? But I'm in the elastic region, so instead of just guessing at this point, I can use the elastic modulus to find the exact number for strain, right? So that's what I'm going to do. And therefore, our stress or our elongation due to the load is elastic, right? Because our strain lies within the elastic region, our stress lies within the elastic region. So therefore, the stress and strain caused to, or the stress and strain due to the load is elastic, or the deformation due to the load is elastic. Lastly, we're going to find stress. We're going to remind ourselves that it is elastic. We're going to use our lovely formula. Young's modulus is equal to stress over strain. Remember, this is only valid for the elastic region. We didn't use it for the total strain and the total the strain due to the temperature increase, right? Because it's not in the elastic region. If we rearrange this formula, we're going to get the stress due to the load is equal to Young's modulus multiplied by the stress multiplied by the strain due to the load. Once you do this wonderful calculation, you're going to get load is equal to 200 gigapascals multiplied by 0.0014 millimeters per millimeter. What you are going to end up getting for the stress cause or the stress due to the load, I need to calculate this because I made a mistake before. 200,000 divided by 0.0014, or not, oh my god, 200,000 multiplied by 0.0014, you're going to get a value of 280 megapascals as your stress due to the load. And remember, the deformation caused, or the deformation that is caused from the stress is, so delta L due to the load is elastic. And these are your answers to this question.